Good evening, everyone. Welcome to day 2 of Pulsar Summit 2021. I'm Ankush Goyal. I'm currently VP of Engineering at Narvar. I've been here close to 2 years now. In the past life, I've also built and operated large-scale reliable systems at Salesforce, Orbitz, and various other companies in growth phase. I'm very excited to be here. A bit around what I'm going to be sharing today. I'm going to go into what we do over here at Narvar and the scale at which we operate, just to set the stage and context. Then I'm going to be talking a little bit about how we have been using Pulsar as our comprehensive messaging and queuing platform over the last 2.5 years plus to solve some of our critical business challenges and some of the learnings and war stories along the way. Just a quick note, some of the things I'll be sharing today might be forward-looking statements, things that might still be in flight. All right, so let's dive in. So what do we do over here at Narvar? We're essentially a platform to enhance customer experience all the way from prior to purchase is made on the checkout page to help convert the customer to once the purchase has been made, engaging the customer from the time an order has been confirmed all the way to them receiving the order. And once they've received the order, we also provide products to help facilitate returns and exchanges. There's a comprehensive suite of our core products throughout that customer journey, all the way from prior to purchase is made to set the right customer expectation, to help convert the customer, to once a purchase has been made, we have a track product to provide tracking of the items and take certain actions like reroute the items to a different address or provide delivery instructions to the courier, to notify product, which help facilitates proactive notifications throughout that order journey, all the way from order confirmation, fulfillment, picked up by the carrier, any delays along the way to delivery. And after the item has been received by the customer, we also provide end-to-end returns and exchanges product, which tracks the item after return has been, which helps facilitates the returns, as well as track those returns all the way to them reaching the warehouse, and afterwards potentially facilitating refund and customer messaging. We also provide this end-to-end visibility into the customer experience to the retailers and their logistics and customer service teams. A bit about our scale of our operations. We've got 1,000+ customers on our platform. Some of the largest retailers in the world use our platform to enhance the customer experience. In order to build this experience, we had to essentially build a whole supply chain of extensive third-party integrations with various carriers, order management systems, warehouse management systems, and so on and so forth. Another data point on our scale, last year we processed over 7 billion shipments through our platform. And by our estimates, about 90% of the online shoppers in US regularly interact with Narvar. So there is a high likelihood that you might have used or interacted with Narvar in some shape or form. In terms of scale of our Pulsar clusters, we currently at our peak times process over 100,000 messages per second. And this number, of course, has been growing super linearly. All right, so let's dive slightly more into how we do all of this. This is, of course, not the comprehensive architecture. This is 50,000 feet overview of how we do things. On the left-hand side, I've represented various different types of integrations that we do. And we get data in various different forms. We get it in batch, we get it in real time, data gets pushed to us. We go and pull data from various different systems. We might do that on demand or on schedule. But once the data comes in into our, we use Pulsar to transport the data. Once the data comes in, we transform the data, validate the data, normalize it, and store it. And afterwards, we check for a relevant state change, which is represented as a trigger over here. Then we would potentially evaluate any rules or conditions that might be configured for that particular trigger, for that particular retailer. And based on the outcome of that evaluation, we might take corresponding set of actions or an action. A good example here would be when a returned item is delivered back to the warehouse and we get a notification for that, we get an event for that from the carrier or from the warehouse management system, then we go and issue a refund by making a call to a third-party API, which might be the OMS system or the ERP system of the retailer. Once that call goes through successfully, afterwards, we let the customer know via an email to expect the refund within a few days. Pretty much all of these use cases can be modeled as given a trigger and a set of rules, take certain actions. This forms the core of our platform, which that is how we get data into a platform to be able to power all of our core products. All right, next up, let's go over some of the business demands and challenges we face and how we have been using Pulsar to tackle them. So first up, we need to be able to provide a single tenant experience on our multi-tenant platform. Some of the constraints we face around that have to do with, first up, variability. You've got tenants of varying sizes in terms of data volume. We've got uber large retailers on our platform doing hundreds of thousands of orders per day, to smaller growing retailers who might be doing hundreds of orders per day and everything in between. The next constraint is around spikes. We've got various third-party data sources that push data to us. In best case scenario, they're pushing data to us in smaller chunks, but in worst case scenarios, they could potentially aggregate the data over days and weeks and send us either erroneously or knowingly in one fell swoop. We need to be able to protect our systems against it, but still be able to absorb it. And lastly, we need to be able to tackle seasonality in commerce, both ups and downs in demand, as well as the significant uptick during retail peak between October to January. All right, so double clicking on variability and how do we tackle it? So let's first motivate the problem. So as depicted over here, we could have various different tenants, A, B, C, and D, all of them sending us data around about the same time. And one of the large tenants, in this case, tenant A, could potentially monopolize the resources, in this case, the topic resources, and starve out some of the other tenants like tenant C and D. Ideally, we want to be able to apply some form of fairness throttling at tenant level to and have a better scenario as depicted under better. One strategy we could have taken is completely separate out the larger tenants into their own environment, but that is operationally hard and costly at scale. So we needed a strategy that can work and scale with our customers while minimizing the operational overhead. We explored between shuffle sharding all the tenants on a fixed set of topics with custom partitioning on the producer side versus per tenant topics. Ultimately, we decided to go with per tenant topics or queues, which I'm using interchangeably right now, due to ease of implementation and granularity of control. In some ways, having single topic and multi-tenancy are really at odds with each other. By the time you have queued up queued up in the shared topic, it's hard to isolate out one workload from another. So using more than one topic really helps us shape the traffic and gives us that granular control over fairness. What makes it very easy to support and scale out large number of topics in Pulsar as compared to something like Kafka is the segment-based architecture of Pulsar, wherein topics are broken into ledgers and segments and distributed across the cluster. And on a bookie, segments across topics get aggregated and sorted into an entry log based on time and size, which allows Pulsar cluster to scale out very easily. So new data can automatically start getting written to new bookies on new segments, and no rebalancing is required. Let's double clicking on how do we handle spikes. In general, there are two approaches to handling it. One is either you need an isolated buffer to absorb the additional spike coming in and release the traffic at a consistent rate to not to overwhelm the underlying network, or rate limiting and applying back pressure. We use both mechanism in tandem. I'll cover isolation later in the talk, but Pulsar provides us granular topic level rate limits, both on producer and consumer side, that we've been able to use and utilize to reduce the effects of spikes. Next up, handling seasonality. This one is somewhat trivial due to the design of Pulsar, wherein brokers and storage can be independently scaled as needed. And secondly, the segment-based architecture that really allows us to scale out without requiring any expensive rebalancing. All right, so that was about how do we provide a single tenant experience on our platform. One of the other business challenge we face is due to unreliable third-party APIs. We've got significant amount of third-party integration, both ingest data as well as egress data. Our contract in most cases is if an API is unavailable during a period of time when we are trying to reach out to it, we'll retry up to a max number of times, backing off exponentially. Initially, we started out with our own complex scheduling functionality to facilitate this. But last year, we switched to using delayed sends functionality provided by Pulsar and cut out the additional complexity from our infrastructure. Last up, as a business, we need to be able to support flexible tenant-specific rules for filtering and conditional logic. For instance, a retailer might have a custom rule on certain attributes of customer that indicate VIP customer versus regular customer, and they decide to take a different set of actions for the VIP customer. We're able to facilitate this flexibility in rules by utilizing Pulsar functions that can be written by our professional services team or by tenant themselves and deployed easily at runtime. One of the challenges we had with Pulsar functions was lack of elastic scalability, but it got addressed with flexibility to deploy on Kubernetes, which we are very much looking forward to leveraging. Next, I'll go over some of our war stories and learnings on reliability of queuing systems. So let me start with a production incident wherein a subset of our webhooks corresponding to a particular transaction on our system stopped going out. As we dug deeper into the issue, we found that Team A had deployed a destructive schema upgrade, Pulsar message schema upgrade to production, which was getting consumed by Team B that was responsible for ultimately propagating those webhooks. Now, Team A thought that they were still testing those changes and had time to orchestrate a deployment of these destructive schema changes along with Team B. But in this release, they pushed a supposedly independent shared library version upgrade to production, which transitively brought in schema upgrade changes inadvertently. Now, apart from the obvious lack of integration tests for this part of the system, the learning over here was the importance of platform level guardrails to prevent against these human mistakes that eventually can and will happen, especially when you've got multiple geo-distributed teams building parts of a complex distributed system, all cooperating to deliver some customer value. So ideally, we do not want to allow any non-backwards compatible schema evolution and avoid the need for complex coordination or orchestration in the first place. We were able to achieve that by enabling forward transitive schema compatibility check in Pulsar schema registry, which fails any non-backward compatible schema upgrades and leads to a fast fail. Now let's talk about backlogs. So in a queue-based system, there are two modes of operation: fast mode or happy path, wherein your arrival rate is lower than your consumption rate on an average. In this mode, you have low latencies overall and high availability. The second mode is the slow mode or the unhappy path, wherein a sudden spike in arrival rate or reduction in consumption rate causes a backlog to start accumulating, which leads to end-to-end latencies going higher and higher, and ultimately takes great deal of time and work to work through that particular backlog and return back to fast mode. In this second sinister mode, work can be completed too late for the results to be useful, essentially causing an availability hit that queuing was meant to guard against. So it's important to try to avoid large backlogs to begin with. The old adage of prevention being better than cure really applies over here. So as you can tell, my next board story is about backlogs. But first, let's take a quick digression on Pulsar read and write paths to give us a mental model to keep in our RAMs. So on the write path, the producer first writes to the buffer, then it writes to the broker that is serving that particular topic. That will then write to an ensemble of bookies that are responsible for the segment for that particular topic at that point in time. Inside the bookie itself, one of the bookie, it will write to the journal, and then it will write to the write cache. And then all the other writes get propagated asynchronously via an async thread all the way to entry log and the index. So that's the write path. Now on the read path, as the consumer is doing tail reads, it's tailing the topic, or even cold reads, it will go to the broker that is serving that particular topic. In a happy path scenario, aka tail reads, broker will find the corresponding message or set of messages in the managed ledger cache as depicted over here, and just serve that traffic, that request from the cache itself. But in case of a cache miss, it will find the corresponding bookie that is holding that particular segment. On bookie, it will first try to find that particular message in the write cache. If that fails, then it will look up in the read cache. If that also fails, then it will look up the index to find the offset and the log, which is holding that particular message onto the disk. And then it will read that data from the disk, from the entry log, and store it in the read cache, serve the read request. So that brings me to my next war story, the perfect storm. So early last year, we had a large production incident wherein backlog started growing and some of the critical ingestion systems started getting throttled. As we dug deeper, we found that this all started with one data ingest integration, bulk uploading multi-week worth of carrier data in one fell swoop, and Pulsar producer for it, happily processing it and writing to Pulsar as quickly as possible. Now we have a natural write amplification in our overall pipeline, wherein one message eventually gets consumed by upstream consumers and rewritten back to Pulsar on separate topics after some transformations. This led to cascading issue wherein spike of messages ended up monopolizing majority of the managed ledger caches across the brokers. So other consumers reads went from being tail reads to cold reads, and now they needed to be served from the bookie and eventually from the disk. So in this case, disk IO became our limiting factor for scaling throughput and to be able to reduce the backlogs and bring the system back to healthy as a whole. We saw that our cluster configs at that point were mostly set up as defaults, which work very well in case of a happy path scenario, wherein all the reads are tailing reads and there are no backlogs, but not so well in case of cold reads. So we had to make some bookie config changes around size of the RocksDB block cache so that we were allocating enough memory to hold significant or majority of the index into the cache itself and avoiding swap in and swap out of index entries. We also adjusted the read ahead cache size so that we were able to, when the reads were going ultimately to disk, those were efficient and they were able to read ahead significant amount of data and bring it back into the cache. And lastly, we also increased the size of our managed ledger cache on brokers. Ultimately, the learning over here for us was to look at the cluster configs with not only the lens of happy path, but also with the lens of unhappy path of spikes, backlogs, cold reads, and making sure that our cluster could handle the worst scenario as best as possible. Another learning from this afterwards, after the issue was resolved, we really strove to minimize the probability of in the future and took inspiration from cell-based architecture to minimize the blast radius. So to reduce the probability of correlated failures, we decided to split our one large Pulsar cluster into 3 Pulsar clusters, one for data ingress of critical data, but that was non-repeatable, aka where there were third parties that were making calls to our APIs. That data was being written down into Pulsar. Those writes from those third parties could not be repeated. Data ingress of critical but repeatable data, where we were pulling the data from another source, and if needed, we could always do a repeat of those reads. And lastly, the overall processing of the data, we separated out processing from the ingest to avoid the probability of correlated failures. We also added rate limiting between ingestion and processing clusters to avoid the overwhelming in case of a spike in ingestion. Another strategy to deal with surges and failures of third-party APIs that can lead to head-of-line blocking is a mechanism to sideline or expire that head-of-line data into another queue that can be processed independently as and when resources are available. Of course, Pulsar provides fantastic support for dead letter queue mechanism to sideline or expire failing messages, and we've been relying on it in production. Now that brings me to my next war story, the story of a poison pill, wherein we had an incident where we started accumulating a backlog on our messaging pipeline with end-to-end latencies going up. As we dug deeper, we found that one of the consumer was stuck on processing a single order, which had over 500 shipments. So it was stuck in an infinite loop where it would receive a message, that poison pill message from Pulsar, send it to processor for hydrating an email template, which eventually would time out, and it will knack back to Pulsar. Now, with manual intervention, we were able to identify and sideline that poison pill message. But curious part here was that we had max retries set up on consumer, and ideally after trying that message up to the max retries, that message should have been sidelined into the dead letter queue, or that was our mental model. But this message was still getting redelivered infinitely by Pulsar. So eventually we found that max redeliver count was not respected in the Pulsar Java client version, library version we were using at that time. And eventually upgrading the library version fixed the issue. Now, really the lesson over here for us was trusting but verifying the functionality of any library that we use or any system that you use. Lastly, a note on measuring availability and latency in asynchronous systems. So a very simple representation of such a system is depicted in this diagram, wherein this is a pipeline that is composed of various async services chained one after another. A message, let's say a message like carrier event for a delivered package might enter the system at the root node, as depicted by the white node over here, gets processed, transformed, filtered on the intermediate nodes, the orange node and the green node, and eventually lands on the terminal node as depicted by the yellow node, which takes an action that consumers ultimately care about. There might be short-lived backlogs in between, and also terminal node might call a third-party, unreliable third-party API that might be down and needs to requeue the message to retry later. So we found that a better metric for health of a system like this is the latency metric of age of first attempt to deliver a customer value. So in this diagram, that would be T3 minus T0. For example, from the time we receive a tracking status update from a carrier to the time we first tried taking a corresponding configured action, like sending a webhook to a third-party API. Measuring latency from the perspective of consumer gives a better picture of overall latency in the system, and is also aligned with the consumer, the actual consumer impact in case of backlogs and delay. Also, measuring first attempt latency instead of measuring all latencies, or rather focusing on measuring the first attempt latency, also avoids the false positives due to unavailability of third-party systems wherein we had to requeue and retry. To wrap up, overall, we have come to rely on Pulsar as the core part of our platform strategy. And although there have been bumps along the road, but having an engaged and growing community and strong partnership with Stream Native has been very, very helpful for us. Thank you, everyone.